Okay, we are ready. So I was looking back at last day, what we kind of went through. Hey, how come it's not? Okay, a little sluggish here. We got into section 4.3, right? And we established that logs are just the inverse of an exponential function. So log base a equals y of x equals y, we can write as a to the y equals x. And then we use that to solve logs. And then I did warn you that we are just going to do these on our calculator, right? So that's not something that we need to be able to do. It's just good to know the mechanics of it all. Right? And so we worked through a couple and we said, okay, well, we've got a common log, which is log base 10, which we usually just write log of x. And so if there's no base, then the base is 10. So that's the common log. And then we also introduced the natural log, which is log base e, which we usually write ln. And so on your calculators, you will have an ln button. If you have a scientific calculator, it's just going to be a matter of finding it. Some calculators even have a log with an empty base button, which mine does. And then you can just calculate logs of any base if you want to. We did say, okay, well, if your calculator does not have that fancy button, right, then how we have to calculate these, or the easiest way to calculate these things, is to use the change of base formula. So I actually sped ahead to section 4.4 to pull this out, just because I wanted to establish how we're going to calculate these, because otherwise it feels kind of like black magic. You know, this to the power of this has to equal this. How are we supposed to know that? Right, and so we can use this change of base formula. So if we want to calculate log base b of x, then what we can do is we can pick another base a and use log base a of x over log base a of b. Notice that these are the same log with the same base, right? And so I always use log base e, so the natural log, because everyone has that ln button. And I say that, okay, if I want to find the log base b of x, I have the ln of x over the ln of b, right? And that's how I can calculate these things if I don't have that fancy button. Right? And we just confirmed it using both ways. We get the exact same thing. So, so that's how we'll calculate these. Okay, so that's kind of too much to write down for review, but that's kind of where we got to. And we'll kind of come back to it in a little bit here. Okay, so we're going to continue. So section 4.3, logarithmic functions continued.
I have a quick question.
Yes.
For the log changing base. When I do like natural log 3, say divided by natural log 14, and just put it in like that,
yeah,
I get a different answer than if I do natural log 3 enter divided by 14, which seems weird.
Okay, so you're doing, you said the natural log of 13 something?
Natural log 3 over natural log 14.
Which, if we had to solve that in logs, that would be log base 14 of 3.
Yeah.
Okay. So then we should be able to do. Okay, so the natural log of 3 divided by the natural log of 14, I get 0.41628966639.
Yeah, so that's what I get if I do natural log 3 enter and then divide by. But if I just do natural log 3 divided by natural log 14, I get 0.1281.
Oh, because I think what it might be doing if you don't close the brackets is it would take the log of 3 or the natural log of 3, oh, whoops, divided by the natural log of 14, like that.
Okay.
Let's see here. The natural log of 3 divided by natural log of 14. So that'll do it. Yeah, and then let me just use that log base 14 of 3. Yeah, I get the same number, 0.41628966639. Just want to make sure I'm not working towards the wrong number. Good. Hey. There's no new handouts or anything, don't worry. Yeah. We're just going to keep working on section 4.3. Okay, so that's how we're going to use the change of base formula. If you don't have that fancy button, if you have the fancy button, you don't need the change of base formula, but it might be good to know just for in general. Okay. So today we're going to just plug away and learn some log laws. Fun to say, fun to do. And then we'll use them to kind of simplify some problems and just talk about logs. So on your 4.3 handout, I'm going to copy the properties of logarithms so that we can talk about them. Okay. So these are general properties that work for the log of any base. But these ones are not going to be, I mean, I'll assume that you know these, but you can just check them on your calculator, right? So these ones, we can kind of write them in shorthand, right? The log of any base of 1 is going to be 0, right? Because remember, the exponential function passes through 0, 1. And then if the log is the inverse of that, right, it's going to pass through 1, 0. So since log base a of x passes through 1, 0, the log of any base of 1, I'll put the of any base in brackets. So the log of 1 will always be 0. The second one, it's got the extra kind of justification on the side, right? But I just kind of want to boil it down into kind of reasons that we are probably more familiar with. So the log base a of the base is going to be just 1. So log base a of a, oops, turned into a mountain range, of a is 1, which says that the log of the base is 1. How we're going to cancel some of these guys is the third property. And so the third property, right, is that the log base a of a to the x is just going to be x, right? And so the log base a of a, we know is just 1. And so that x, I think of it as it just drops down, right? And so that's going to be a way of canceling that x. We'll see why in the next section, I think, why that is. We can kind of scan ahead. but by the properties, so by the log laws, which are in section 4.4, one key thing that we can do is we can rewrite. So if we're taking the log of an exponential function, what we can do, and this is how we're going to solve for x, is the log laws say that we can rewrite this as the x in front. So x times the log base a of a. And then previously we said that the log base a of a is 1, right? So then we have x times 1 is x. Right? So we'll see how those link up in a little bit here. But for now, right, we can kind of bring the power down by taking the log of the same base as the base of the exponential function. Whoa. The log of, can I just call it the log of the base? Cancels, leaving only x, right? And like I said, we'll see why that is with the log laws, but let's do a little kind of side note here. So if I have e to the 2x, right, and I take the natural log, which is log base e of e to the 2x, I'm just left with 2x, right? I'm just left with everything in that power. And so here, that's how we're going to simplify things, right? If we have e to the 2x or just any a to the 2x, we can take log base a of that, and then it'll drop down. This is how to cancel, and I'm kind of using cancel in a weird way here. How to cancel the e. Remember that the exponential function and the log, they're inverses of each other, right? So they undo each other. And then the fourth one is that a to the power of log base a of x is just going to be x. So that's the opposite of the one that we just did, right? First, we started with some a to the x, right? And then we took the log base a of that to get x. And now we would have started with log base a of x, and we're trying to shake out that x. So we raise it to the power of a. And so, a to the log base a of x. A to the log base a of x is just x. Raise log base a of x. Other way around. Raise a to the power of log base a of x to solve for x. Key is that you've got that same base. Okay. So those properties, we just have to know our way around. We just have to have them in here. You can check them on your calculator though, so it's not going to be something major. As long as we've got a good handle on the third and fourth one, right, that we can undo some a to the x to solve for x if we just take the log base a, or if we have log base a of x and we want to solve for x, then we raise a to the power of log base a of x. So, any questions before we talk about the domain of a log? Let's do it. So the domain of a logarithmic function before, right, things that we've been keeping an eye out for in our domains is, well, we can't divide by 0, but we also can't take the square root of a negative number. Now we're going to add a third thing to keep an eye out for, and that's that we can't take the log of any base of a non-positive number. So that includes 0. We can't take the log of 0. We have to have a positive number in our log, right? So we can't take a negative or 0.
It has to be a natural number?
Yeah, are those the natural numbers? 1, 2, 3. Yeah, that's how we count. Yeah. Yeah, nice. Wow. Look at you go. Yeah, at least I'm pretty sure that's how I remember it, at least. Could be wrong. Yeah, natural numbers, how we count. Yeah. 1, 2, 3, 4, 5. It can take on values in between those, right? But so not just those integer values, but yeah, still good. So just for review, right? When finding domains, we need to consider the facts that we cannot, 1, divide by 0, right? And we said that any value that makes us divide by 0 is not in our domain. And we can't take the square root of a negative number. We actually can't take the even root of a negative number, but it's okay. We'll talk about the square root. So now, what's new is that we can't take the log of a non-negative number. We can't take the log of a non-negative number, a non-positive number, of a non-positive number. Which means no negatives, which is what I was thinking about, and not 0. So we have to add that to have a third item on our list when we're checking for domains. Right? So if we want to find the domain of some functions, let's see here. Did I have? Yeah, we can move to the next page. So we've already talked about the common logarithm. There's a worked out example just solving with logs, but we'll do some of these on the side on the next page instead. We've also already talked about the natural log. Just kind of referring to the sheet here, 4.3 notes. So we've got that example down in the right-hand corner. And then we talked about the natural logs already. So we kind of sped ahead, jumped around a little bit, not too bad. we can apply the same properties of natural logarithms, but a natural logarithm is just a log base e, right? So it's a special case. So all those properties are the same, right? So there's nothing new here. But what I want to do is look at the domains. Hey, that's not the domain. No, we can go back to that one. I thought I had the, oh, the next one. Thank you. Thank you. Just kind of going back to the one that I kind of breezed over here. You can solve those either on your calculator, right? Or I think what we'll do is we'll come back and solve some of those after we look at the domain. So, oh, copy. It was a two-part. You can't see it, but sometimes it goes like that. Okay. So if we want to find the domain of these things, then we can start a little bit slower, right? And we can look at 73, and then maybe let's jump to, or should we do all the evens maybe? Let's do it. 74. And I want to do quite a few in here just because it's going to be important for us to know how to find the domain. So 74, if we have f of x is log base 5 of 8 minus 2x, if we're just finding the domain, right, then all we need to make sure is that 8 minus 2x is greater than 0, right, and not equal to 0. So for the domain, we need 8 minus 2x to be greater than 0. So we can solve this, right? As long as we're not multiplying or dividing by a negative number, then the sign just behaves like an equal sign, right? If we're dividing by a negative, then we have to flip that sign, right? And so we have to be careful there. But if we go just 8 has to be greater than 2x, and then I'm dividing by 2, that's positive, so then 8 over 2, so 4 has to be greater than x, or x has to be less than 4, which makes sense, right? Because if we do 8 minus 2 times 3, for example, 8 minus 6, that works. It's still going to be positive, but try an x larger than 4, 8 minus 10, then I get a negative number, which is a no-go, right? So then my domain is that x. Usually we like to have just the way that we read it, right? So x on the left-hand side. So the domain is, and we can do set notation if we want to, but honestly, if I'm marking this and you left it at 4 greater than x, you're done, right? But we could say x such that x is less than 4. Fancy set notation. How about 76? So 76 is that the natural log of x minus x squared. So now we've got x and x minus x squared. So the domain here is that x minus x squared has to be greater than 0. One thing that I could do is I could factor out a common x, right? Just to see how this thing behaves. So x times 1 minus x. Well, I can factor that out. Nothing's changed on the right-hand side. Still has to be greater than 0. If I look at this, right, then I've got x and 1 minus x, and I'm multiplying those things. So, and we saw this before. I can't remember the exact, I think when we were graphing from chapter 3, right, the very end, at the beginning of last week, right, we were graphing, and we said, okay, well, if x is negative and 1 minus x is negative, right, then a negative times a negative still makes a positive, right? So that's still safe. And so what we've got here is we've got, okay, well, x has to be greater than 0 if 1 minus x is greater than 0. And so we've got these cutoff points at x equals 0 and x equals 1, right? Because that's where things are going to change, right? So here, right, if we think about where this thing equals 0, right, that's going to be easier to deal with, right? And then we can figure out, we can use a sign diagram or a sign graph or a sign chart to figure out where this thing is going. So here, temporarily, oops, temporarily, let x times 1 minus x equals 0. To see how the signs behave. Right, and so x times 1 minus x equals 0 if x equals 0 or x equals 1. We can use a sign or a sign, what do they call it? A sign chart? I think so. To figure out where this thing is positive. To figure out where x times 1 minus x is greater than 0. So if we've got kind of transition points at 0 and 1, right, what I'm going to do is I'm going to pick some test points in each of these sections. And whether you want to think of it as just the signs of these values, sometimes that's easier, right? And so I could pick values like -1, I don't know, 0.5 and 2, right? Remember the pink one is it doesn't matter which values you pick as long as it's in that the right range. So here for this first part, x less than 0, well, x is going to be less than 0, so it's negative, right? So -1, for example, is going to behave like all the other ones on the left side of 0, right, or less than 0. And so what we have is we have a negative number times 1 minus, and then a negative number makes a positive number, right? And so what I have is I have a positive number, which is negative. So then it's a no-go here, right? 1 minus -1 is 1 plus 1, which is 2, so it's positive. So here, what I know is that x less than 0 is not in the domain. right? Because I can't plug in. In fact, I'm going to include 0 here, x less than or equal to 0, just because we can't have 0 in the log, right? So we have to exclude 0 and 1 because they make it 0. So now we can move on to the next little section here. Now I've got positive 0.5 times 1 minus 0.5 all the way up to 1, not including 1. That's going to be a positive value, a positive times a positive, right? So I've got a positive times a positive, which gives me a positive value. So x between 0 and 1, not inclusive, is in the domain. Is in the domain. And then moving over here, I've got a positive number, right? 2 times 1 minus 2. 1 minus 2 makes a negative number. And so I've got a positive number times a negative number, which is going to be a negative number. So I know that this is not in the domain. So x greater than or equal to 1 is not in the domain. So the only section that works is if x is between 0 and 1. Therefore, the domain is the set of x's such that x is between 0 and 1, not inclusive. Or I know WebAssign loves interval notation. I think it's just because it's easier for it to process, right? So it's easier to enter and it's easier to process. And so, or in interval notation, from 0 to 1, round brackets. That's way easier to kind of handle. That's a biggie. Let's do 78. Do we want to do? No, we'll get the same feel from 70. I was looking at 77 if we should do it, but you're going to find that x has to be greater than 0 and then 2 minus x has to be greater than 0, but then you can only look at the overlap. But we're going to have the same situation in 78, so let's just do 78. Just more complicated. 78 says that h of x is the square root of x minus 2 minus the log base 5 of 10 minus x. So what we have here, right, is that x minus 2 has to be greater than or equal to 0, right? We have to take the square root of a positive number, but we can take the square root of 0. It's just 0. And then here, for this portion, 10 minus x has to be greater than 0. Okay. And in between here, we have to find the overlap, right? Because both of these have to be satisfied in order to be in the domain. And so for our domain, put it down here, we said that x minus 2 has to be greater than or equal to 0, which means x has to be greater than or equal to 2. And you can just do some check-in points, right? 3 minus 2 is 1, so that's positive, so that's all good. And 10 minus x has to be greater than 0. Right? It can't be equal to 0. So then we know that 10 minus x, we can move the minus x to the right-hand side. 10 has to be greater than x, right? Just adding x to both sides. And so if x has to be greater than or equal to 2 and x has to be less than 10, right? So just reading or writing these how we read them, right? X has to be less than 10. And you know what? I'll do them on the side, kind of like a, oh, I didn't want to rewrite that one. Never mind. X, it has to be less than 10. 10 minus 11 makes a negative. That's bad. 10 minus 9 makes a positive. That's good. So it makes sense, right? You kind of want to check in and make sure that what you're saying works, right? Just do little quick test points. So now what we're saying is that x has to be greater than or equal to 2. So if we talk about this on a number line, right, it might be easier to kind of visualize. So we've got 2 and we've got 10 here. And we're saying that x has to be greater than or equal to 2, right? So we have to move from this way inward. Square brackets because it's, I'll do it because it's inclusive, right? Or if you do a solid dot or something like that. This is just for you to visualize, so there's no proper way to do it or real way to do it. But we're also saying that x has to be less than 10, right? And so not including 10, so I'm going to put a round bracket here, but it has to be going in here, right? And so the region including 2 and going up to 10 exclusive, that's our domain. So therefore the domain, and let's start with just fancy set notation. X has to be greater than or equal to 2, but less than 10. Or in interval notation, which I'll just abbreviate IN for now, square bracket 2 up to 10 round bracket. So that one I would say is actually a little bit more mellow than the one we did previously. Any questions about those? So you can add that third criteria to your roster that, okay, we can't divide by 0, we can't take the square root of a negative number, and I can't take the log of anything less than 0, right? Which includes 0. All right. How about, I want to do, let's do 98 and 99. 98 because it's even, but also 99 because it's actually a really cool tool that you can use. So 98. Oops. Oh, gonna crop this thing. Sometimes I feel like I'm fast at working this thing, but other times not so much. Okay. So a certain strain of bacteria divides every 3 hours. If colonies started with 50 bacteria, then the time t in hours required for the colony to grow to n bacteria is given by this formula, right? What's more likely and what we're working towards later is that we'll have a formula that's in the same shape as what we were looking at earlier with the exponential functions. But now we've just got this formula for t, and we want to find the time required for the colony to grow to 1 million bacteria. So now we're just given n, right, to grow to 1 million bacteria, so n is 1 million, and we just have to solve for t. So this is just an exercise in using logs to solve problems, right? And so we've got t is 3 times the log of n over 50. Log is the log base 10, right? So you should have a log button on your calculator, over the log of 2, where n is 1 million. 1 million. So t is 3 times the log of 1 million divided by 50 over the log of 2. So if I solve for 1 million, 1, 2, 3 divided by 50, I need the log of 20,000. So log base 10. Right? I'll make a note of that here. That this is log base 10, the common log. So I want to take log base 10 because I have to specify, but you probably don't, of 20,000. T is 3 times, and I'm going to keep all my decimal places in my calculator, right? 4.301029996 divided by the log of 2. So the log base 10 of 2 divided by 0.3010299957. I better do it again. Okay, times 3 divided by, and then in brackets. Oops, didn't like it. Divided by log base 10 of 2. Keep saying syntax error. Okay. Now I get 42.863. Is that what you guys are getting? No? Let me write it down and then I'll double check here. 863137114. Let me see here. Log base 10 of 20,000 divided by the log base 10 of 2 times 3. I'm still getting that.
Okay, now I got 42.8.
Cool. Yeah.
I don't know, before I was like breaking up all the steps and then when I just put it all together.
I know what I find is it's actually easier. So I wanted to show the 4.3 and the 0.3 just so that you can check your work. But I actually find that it's safer if you just go from the top, which is pretty rare in math, right? Like usually it's safer the more we break it down. But when we're using our calculator, for some reason it doesn't, I don't know, like mine was giving me grief too. So I don't know what it didn't like. But usually if I just put it all in, it'll just do it. So yeah. Okay, cool. How about, so that's the end of that. How about we work on this super cool one, 99, because this is actually a real thing. It's called the rule of 72, and we could go through and we could I could show you how the rule of 72 works. It's just 72 divided by the rate as a percentage. But this is going to make more sense because what we have is we usually have to convert our percentages, so our interest rates, to decimals, right? And so it makes more sense if we just continue using decimals. But so the time required to double the amount of an investment at an interest rate R compounded continuously is given by, so this is at continuous compounding. It actually works for pretty well any compoundings, but I think it's the log of something slightly different, I want to say. No, maybe it is 2. Natural log of 2. The reason I'm pausing is if you take the natural log of 2, you get 69.3 if you convert that to a percentage. I know that's not obvious, but the rule of 72 uses 72 instead of 69.3. So they're very similar, right? But the idea is that regardless of how much money you have, whether that's $10 or $10 million, right? If you invest it at some rate 6%, right, then we can use this formula, this very simple formula, to figure out approximately how long in years it'll take to double, right? For $10 to go to $20, or 10 million to go to 20 million, right? It doesn't matter the amount that we have that we need to double. This formula is just going to do it, right? And so where t is in years, so t in years, right? And r is a percentage as a decimal, right? So r is the interest rate. And so if we let r be 0.06, for example, 6%, then whatever we're investing, t is the natural log of 2 over 0.06. So t, now the natural log of 2 over 0.06, it's important to start recognizing that this is the exact answer, right? Once we take the natural log of 2 and divide it by 0.06, we're only going to get decimals, right? Decimal approximations. And so the difference between an exact answer and a decimal is, well, now we're approximating, right? As soon as we're into decimals, unless we get, 0.5, something nice, 0.128, something clean, we consider decimals approximations. So here I'll just put this is the exact answer, because that is a number. It's just not very obvious for us to interpret. So if I do the natural log of 2 divided by 0.06, 11.55245,301 years. And you know what? I'm going to change this because I know that's not actually equal to. I'm going to switch it to the squiggly equals just to emphasize that this is an approximate answer. So it'll take roughly 11.5 years for any amount to double at 6%. So therefore, it will take roughly 11.5 years for any amount to double at a rate of 6%. Let's do 7% and 8% just to hammer it home. So if we let r be 7% or 0.07, then t is the natural log of 2 over 0.07. That's our exact answer. And our approximate answer is going to be the natural log of 2 divided by 0.07, roughly 9.9, oops, 9.902102579 years. Of course, usually it says, you know, round to 2 decimal places or something like that, but I'm not gonna, oops. Oh, it doesn't say. How about 8%? Squeeze it on the same page here. Let R be 8% or 0.08. Right, so it takes less time for at 7%. I'm expecting it to take less time at 8%. How much less? Let's see here. T is the natural log of 2 over 0.08. And I'll keep it on the same page here. The natural log of 2 divided by 0.08, 8.664339757 years. Nice. Cool. All these money equations, I mean, yeah, they're fun because it's kind of applied, and they're not that tricky, I don't find. And they're useful just for real life stuff. Great. Any questions before we go to 4.4? Let's do it. 4.4 is called the laws of logarithms, or log laws, which is kind of fun to say. So log laws are going to be really important that we just know and use, and just kind of know how to manipulate logs to get to what we want. There's a lot of fields where we need to take logs of things just to kind of, well, one in stats, we have to kind of take logs to straighten things out. And so, and I'll show you how in a little bit here, but there's a lot of fields where we need to take logs and work with logs. So let us talk about the log laws. Okay, and there's a warning on the side of your page too, right? Don't go making up log laws. And you can read that warning on your own. But here are the rules that we've got. First rule is that if you've got A and B being multiplied by each other inside a log, how you would expand that and separate A and B is that you actually end up adding the logs of the same base, right? So the base of the logs always stays the same, it never changes. And so if you're multiplying inside, then to split those up, we actually add them, which is way different from what we're used to doing, right? If we're multiplying, we end up multiplying outside, but for logs, it's different. If we've got log of A over B, so if we're dividing inside, then we end up subtracting on the outside when we split these up, right? And so, and then here is that property that we already kind of talked about, touched on, is that the log of A to the power of C can be written as C times the log of A, right? And so this is how we're going to be able to bring that power down. So we need to know/memorize these log laws. And the third one, and the third law is especially important. Right? The fact that the log base a of a to the power of c is the same as c times the log base a of a. Essentially, right, we've had this c and it just gets dropped in front. This was a while ago. I feel like it was last day or maybe the day before. No, I feel like it was Friday. We were in the portable. I always have to think of where we were when we were talking about stuff. Where we said, okay, well, how long is it going to take for this population to grow to some amount, right? And so not an unreasonable thing to want to solve for, right? Right, and so here from last day, we were solving for the population growth, I think, or the spread of a disease maybe, right? And then we worked through this all, and then we got to this point, and because we had t in this power here, we said, okay, well, we don't know how to solve for t in the power. Right? So in general, we use logs to bring that power down, right? If we have a variable in the power, we need to take logs to bring it down in front, and then we can solve for it. Right? And so going back to what we were just talking about, right? If I want to solve for c, then, and I don't have this on here yet, if I take the log of it, then I know I can rewrite this as c times the log of a, right? And so this is kind of a, oops, it's a different color. To solve for values in a power, we take the log to bring the power and then quote unquote down, right? So we take the log to bring the power down. Right, I'll put quotes around that. And this is going to be really a very important concept. And this is why we need logs, right? Is so that we can bring those powers down and to solve for them. Right. Usually, I end up using the same base as what I'm working with. So for example, can't remember exactly what it was, but if I have e to the negative 0.97t equals 4, for example, to solve for t, we take the natural log of both sides, right? Because I've got e to the power, so if I take the natural log of e by those rules, I know I get 1, so then that makes it easier to deal with. You absolutely could take log base 10, but then it wouldn't cancel. You'd have log base 10 of e, and it just doesn't look good. So to solve for t, we take logs of both sides, right? Whatever we do to one side, we have to do to the other side, right? To keep it. Otherwise, we can't have an equal sign in there if we're not keeping them equal. And so to solve for t, we take logs of both sides. Usually natural logs. I will always use natural logs. And what's nice is that it will always work, right? And so for me personally, I'll just use natural logs. I'll put that in the side note here. I will always use natural logs. Even if my base is not e in my power, I'll still use natural logs, because whatever. So what we do, right, is we take the natural log, and remember I write my natural log as just that squiggly ln of e to the negative 0.97t, and we're just pretending it's equal to 4, so then I want to take the natural log of 4. So here, this is what's important, right, is that this t actually goes down in front here, right? And that's how actually the whole 0.97 or negative 0.97t can go out front. The whole power goes out front.
And then it's just a 1, right? It would be negative
That's right.
0.97t times 1.
That's right. I'm still going to write it in this step, but if you skip straight to just ignoring the 1, right, it dissolves, that's fine. So then we've got negative 0.97t times the natural log of e is the natural log of 4. Don't forget that natural log of 4, right? Because it's going to help you in solving this thing. So you get negative 0.97t equals the natural log of 4. Solving for t, I get t is the natural log of 4 over negative 0.97. Now in this case, it doesn't really make sense to have a negative t, but that's okay. The natural log of 4 divided by negative 0.97, t is roughly equal to negative 1.4291694444. This was just an example we made up, so, or I guess I made up. I'll take the blame. T is usually not negative. I mean, it can be, but often it's not. So, but that's how we're going to use it, right? To bring that variable down that we're trying to solve for in front, we have to take the log of both sides. And so we can also use the log laws to expand and simplify, and let's have a look here. And there's some examples on your handout, but we can just go to some of these and do them. So if we want to use the log laws to expand some of these guys, right, so now we're not solving anything quite yet here. I think we just did, but let's see. Let's go for some of these heavy hitters. Maybe let's do 46 and 48. How about that? So if I do 46, and if I want to expand this, log of x over the third root of 1 minus x. You're going to start from the outside and work your way in. And so here at its core, I've got a fraction, right? X over the third root of 1 minus x. And so if I've got a fraction inside, then I can split this up by subtracting the logs of the same base. And we're working in log base 10 because it's just logs. So I'm going to do log of x minus the log of the third root of 1 minus x. And let's see here, that's log number 2, or law number 2, log law 2. I'll put it over here. Which rule? That's not something that you have to do. I just want to kind of highlight which rule I've used at each step. I can simplify it a little bit more, right? Because 1 minus x, the third root of 1 minus x, I can write as 1 minus x to the power of 1 over 3. Right? The log of x I can't do anything with, so I've got the log of x over here minus the log of, and then 1 minus x to the power of 1 over 3. That's not really a log law that I'm using. It's just a fact, right, of powers and roots. But now I can simplify this a little bit, right, and bring that 1 over 3 down in front of the log of 1 minus x, right? And so then I have the log of x minus 1 over 3 times the log of 1 minus x. And this is using law number 3. And that's as simplified as we can go. Should we do 47? What do you think? Yeah. Oh. No flights to Italy. Crazy. 47. Okay, it's a biggie. I've got the log of the square root of x squared plus 4 over x squared plus 1 times x to the 3 minus 7 squared. Wowzers. Same thing, right? You're going to approach it from just kind of bird's eye view. Okay, first of all, I've got a fraction that I'm going to split up, and then I'm going to look deeper. So I've got the log of, oh, I've got that square root I can't forget about. Aren't you glad we're not finding the domain of this thing? Don't worry, I wouldn't do that. That's so mean. I forgot about the square root, right? How am I going to rewrite the square root? I'm going to rewrite everything to the power of 1/2. Then I'm going to be able to bring that out in front, right? And then we have to be careful. So what I've got is the log of x squared plus 4 over x squared plus 1 times x to the 3 minus 7 squared to the power of 1/2. So far, no log laws have been applied. But if I write 1/2 times the log of x squared plus 4 over x squared plus 1 times x to the 3 minus 7 squared, then I've used law number 3, where I've brought down that power in front, and now I don't have to deal with that, right? Now I can break up these logs. And because I've conveniently got a page break here, I'm going to shift everything over to this side of the page because I'm going to need a lot of room. Remembering that 1/2 is multiplying everything, right? And so what I'm going to do is I'm going to put the 1/2 outside these big square brackets, just to make sure that I remind myself that it's multiplying everything. Now I can split this up as a fraction, right? Because I've got the x squared plus 4 over x squared plus 1 times x to the 3 minus 7 squared. And so what I've got is I've got log of x squared plus 4 minus the log of, and then inside more brackets, x squared plus 1 times x to the 3 minus 7 squared. And then that's the end of the square brackets. And the rule here that I used is rule number 2, or law number 2. Okay. So far, so good. Don't be deceived, right? This is where that note about don't try to make up log laws about adding inside the logs. There's no such rule, right? And so if we're adding inside here, there's nothing else that we can do. We can only handle multiplication and division inside, right? And so But if we move on to the next log, right, I can still break up that next multiplication, right? X squared plus 1 times x to the 3 minus 7 squared. And so I can still break that up. This thing's going to get huge. 1/2 is on the outside. I can't do anything with log x squared plus 4. Minus, and then what I'm going to do again is I'm going to put square brackets just to remind myself that that minus is on the outside of everything here that I'm about to do, right? Because what I'm going to get is I've got the log of x squared plus 1 plus, and I'll do it in 2 steps, the log of x to the 3 minus 7 squared. This is law number 1. If I'm multiplying inside the logs, then I can add them if I break them up. Okay. There's nothing I can do on the x squared plus 1 inside the log, right? I'm done. But there is something, I could bring that power of 2 down in front, and then I would be done after we simplify. But let's see here. We've got 1/2 all times, oh, I forgot a square bracket here. All times the log of x squared plus 4 minus the log of x squared plus 1 plus 2 times the log of x to the 3 minus 7. Square bracket, square bracket. And there I used law number 3 again. Okay. I can simplify this a little bit, right, by bringing in that negative, but other than that, there's nothing that I'm going to do here. I'm just kind of stuck. Even if you ended here, that would be fine, right? But I'm just going to get rid of those square brackets on the inside at least. And so I get, oops, I get 1/2 times the log of x squared plus 4 minus the log of x squared plus 1 minus 2 times the log of x to the 3 minus 7 and square brackets. And then we could bring in the 1/2, of course, but I'm going to leave it out. Cool. So log laws, I kind of, what's that instrument? It's like an accordion. Yeah, exactly. So log laws, I think of an accordion, right? You can either compress things or you can expand things. So right now we're expanding things. And then of course we could do the reverse, and we will, where we kind of compress things into 1 or 2 logs instead of all these logs here, right? So we can kind of work forwards and backwards. But let's do 48 as well. 48, we want to take the log of the square root of x times the square root of y, which is times the square root of z. Whoa. Just simplifying this is a little bit weird. I'm going to have to rewrite all these in terms of powers, right? These square roots. And so if I have the log of, and I'll just, I guess I can start there. This all equals the log of, and I'll start inside and just move my way out, right? And so here I've got the square root of x, that, and then the square root of y, but I'm going to rewrite z to the power of 1/2 in there. And I write little kind of down ticks on my square root at the end just to show what's inside my square root. Might be helpful. So then the log of the square root of x times y times z to the 1/2 to the power of 1/2. Right? Noticing that y and z to the 1/2 are all to the power of 1/2. Same thing with the x, or the root of x. We've got the log of, and then x times y times z to the 1/2 to the power of 1/2 to the power of 1/2. Whoa. What's nice is that I'm multiplying inside here, so I am allowed to distribute this power, right? Because I'm multiplying, I'm allowed to distribute the power. Since we are multiplying, we can distribute the power. Right? But before you go and distribute a power, I do want you to convince yourself that you're allowed to do it, right? Because if we had x plus 1 squared, that's not the same as x squared plus 1 squared, right? We know that's x plus 1 times x plus 1, which is going to be x squared plus 2x plus 1, right? So it's not going to be the same. But if we have x times 2 squared, that is x squared times 2 squared, right? So that's the truth. So that's what I mean by distributing that power. You're allowed to do it because we're multiplying. So what I'm going to do slowly but surely, right, is just kind of bloom out from the inside and just get away with, or do away with a lot of these extra powers. And I'll scoot over just for some more room. So I've got the log of, I don't need a big bracket like that, just like this, of x, and then on the inside here, I've got y to the 1/2 times z to the 1/2 times 1/2, right? Multiplying fractions, 1 times 1 is 1, 2 times 2 is 4, so I've got 1 over 4, and then that is going to be to the power of 1/2. Now I can distribute that 1/2 onto the x, the y, and the z. So now I have the log of x to the 1/2 times y to the 1/4 times z to the power of 1 over 8. Now, whew, now I'm multiplying in here. So then I can say, okay, well, and it applies to more than 2 things being multiplied, right? And we just keep adding these logs if we break them up. And so here we get the log of x to the 1/2 plus the log of y to the 1/4 plus the log of z to the 1/8. And so here, this is law number 1. First law that we've used, I think. Yeah, we just had to simplify to get there. And I can rewrite this, right, bringing that power down in front. So I get 1/2 times the log of x plus 1/4 times the log of y plus 1/8 times the log of z. And that's by rule number 3. And then that's expanded and simplified. Oh, that was a biggie. Any questions about those ones? No? Just takes practice. What if we want to go the other way? right? What if we want to combine these? And so now, as long as we're working in logs of the same base, we're able to combine these things. And so if we look at 49 to whatever that number was, to 56, oops. If we want to combine these expressions, right, as long as the logs are of the same base, we can work in reverse to combine logs. Now I actually find that going this way is a little bit easier. And so let's do 54 and 56. How about? Or maybe 55 too. But I do have to kind of, let's do 54. But this is important, right? This is kind of one of the main things that you need from this course, even though we don't get to spend a lot of time on it, but it is important. So 54, we've got log base 5 times of x squared minus 1 minus the log base 5 of x minus 1. Because I've got log base 5 on both of these, I am able to combine them. And because I'm subtracting, I know I'm just going to have the log base 5 of x squared minus 1 over x minus 1. So that one's not bad. X squared minus 1 over x minus 1. And I can still say which law I use. This is law number 2, just in reverse. $55. Now we've got the natural log of a plus b plus the natural log of a minus b minus 2 times the natural log of c. Okay. If I'm adding logs, right, regardless of the base, then I end up multiplying what's inside. And then if I'm subtracting, then I'm dividing. One thing that I am going to do is I'm going to bring that 2 times the natural log of c to make the natural log of c squared, right? Just kind of reversing everything that we were doing before. And so, and I'll make myself some more room here. So I've got the natural log. The only thing I'm changing is bringing that 2 up into the power of a plus b plus the natural log of a minus b minus the natural log of c squared. Right, this is rule number 3. Now, these are all log base e, right, the natural log, and so I can write the natural log, oops, the natural log on the outside. And in the numerator, right, because I'm adding a plus b and the log of a minus b, I get a plus b times a minus b. And then I'm subtracting the natural log of c squared, so then I'm dividing by c squared. And this is a combination of number 1 and number 2.
Is it necessary to combine those 2 top terms, or is it fine the way it is?
It's okay the way it is, I would say. Yeah, we're not really going to gain anything, right? But a squared minus b squared, it's not going to cancel with the c squared anyways, so I would just leave it. It's good. Nice. Okay. How about 56 then? If we've got 2 all times the log base 5 of x plus 2 times the log base 5 of y minus 3 times the log base 5 of z. Oy. They're all log base 5, so that's good, right? I can combine these eventually. But what I will do is I'll multiply that 2 inside just so I don't have it multiplying everything else, because otherwise there's nothing I can do with it. But I can expand that 2 in, and then my next kind of order of business is going to be to rewrite all the coefficients of the logs as powers, right? And so what I get is this is 2 times the log base 5 of x plus 4 times the log base 5 of y minus 6 times the log base 5 of z. So now I'm going to bring all those, I'll call them coefficients, up into the powers. So I get the log base 5 of x squared plus the log base 5 of y to the 4th minus the log base 5 of z to the 6th. And I'll just put a note here that this is by law number 3. Okay, this is the same situation that we just had, right? I'm adding 2 logs and then I'm subtracting them. If I'm adding them, then they're multiplying. If I'm subtracting one, then it goes in the denominator. And so because I have log base 5 on both sides, I've got the log base 5 on the outside, and then x squared y to the 4th over z to the 6th. And this is by number 1 and number 2. Make this z look more like a z. So we do have to be fluent in moving back and forth, right, between these logs. But other than that, once we kind of get the hang of it, then it's okay, right? And we do need to have those log laws in here, kind of memorized, or at least, like I said, just fluent in these things. We already talked about the change of base formula, so I mean, can have a look. How about we do the change of base number 66? Sure. We already did this one, so let me see if there's, okay. I'm gonna keep it on the same page here. 66, well, I said that I would use the change of base formula just using the natural logs. If you prefer the common logs, log base 10, that's fine. Just use one that's on your calculator and it doesn't matter. If we want to solve the log base 12 of 2.5, that's going to be the same thing as the natural log of 2.5 divided by the natural log of 12. Which we can do. So the natural log of 2.5 divided by the natural log of 12, I get is roughly equal to 0.3687425167. And I can just check it with my fancy button here. Log base 12 of 2.5 is 0.3687425167. Phew. But we already did that, so work through that. But just make sure that you've got all those down. Okay. Any questions before we get to actually solving these things? Okay, so section 4.5 is where we actually get to apply these logs and exponents. And in general, right, we've already seen it. We ended up kind of working through how to solve one of these things. But if you're solving for, you know, something in the power, then you're going to isolate the value and that's in the power, and you're just going to apply logs to it, and then there you go. So 4.5 is called exponential and logarithmic equations. You've got it on your handout. Oh, not in section 4.4, it's in 4.5. But I'll just bring it in so we've got it. So if we start by solving exponential equations, then the first thing we have to do is we have to isolate the exponential expression on one side of the equation, meaning we have to move everything else over to the other side, right? And then you take the logs of each side, right? Because that's how we're gonna kind of dissolve the exponent, right? And then the power drops down by those exponent laws or the log laws, or even the laws of logarithms, depending on what you're talking about. And then we can solve for the variable. Right? And we already did a quick example of that. So here we go. Let's just grab a copy. So if we do maybe, which one looks good? Let's say we want to do 37, no, 36 maybe. Let me stick to the evens, how about? Let's do 37 and 38. Sorry, I said 37, I meant 36. So 36, 7 to the power of x over 2 is equal to 5 to the power of 1 minus x. I want to solve for x, and they're both in the powers. There's nothing I can move over or do here, right? The only thing that I can do to bring those x's down is to take the log of both sides. And I always take the natural log. And so what we have to do is we want to solve for x. So if I take the natural log of 7 to the power of x over 2 is equal to the natural log of 5 to the 1 minus x, as long as I take the log of both sides, right, nothing's changing in this equation. But now I can use the log laws to rewrite this as x over 2 times the natural log of 7 is 1 minus x times the natural log of 5. And just to remind ourselves, this is by rule number 3. We said that that was going to be a heavy hitter, right? If we're solving for things in the power, then we take logs, and that's why we need them so bad. Now, I've got x's down where I can work with them. And so now it's just a matter of solving. So if I kind of bring that 2 over, I get x times the natural log of 7 is 2 times, well, actually, I'll simplify this first, is the natural log of 5 minus x times the natural log of 5. Just to bust it out, because I am trying to solve for x. So ideally, I'm going to try to migrate all my x's over to one side and my numbers to the other. Now I can multiply both sides by 2. And I could have earlier too, but it just got a little messy. So now I've got x times the natural log of 7 is 2 times the natural log of 5 minus x times the natural log of 5. I can distribute that 2 in front, so I get 2 times the natural log of 5 minus 2x natural log of 5 is going to be x times the natural log of 7. Moving my x's to the left-hand side, I can add both 2x log 5 to both sides, and so I get x times the natural log of 7 plus 2x times the natural log of 5 is 2 times the natural log of 5. Now I can pull out that common x on the left-hand side, and I get x times the natural log of 7 plus 2 times the natural log of 5 is 2 times the natural log of 5. Don't be discouraged because the log of 7 and the log of 5, those are all just numbers, right? They're just kind of nice and compact right now. So x is going to be 2 times the natural log of 5 divided by, right, the natural log of 7 plus 2 times the natural log of 5. This is the exact answer. That's a number. Once we plug that into our calculator, we get the approximate answer. And so I have roughly, here we go. Let's see if I can pull this together. I'm going to use my brackets carefully. 2 times the natural log of 5, but I am going to do it all in one go. Divided by, and then bracket the natural log of 7 plus 2 times the natural log of 5. Okay, make sure you, let's see if we get the same thing. 0.62323580849.
Yep.
Cool. So this is the approximate answer. I'm only highlighting that because that's going to be important that we realize that decimals are just approximations, but also if it asks for the exact answer versus the approximate answer. Nice. How about we do 38? So 38, we've got 10 over 1 plus e to the negative x equals 2. So what we want to keep in mind, right, is the first step is that we want to isolate e to the negative x, right, because we want to solve for x, but we want to isolate e to the negative x. So whatever we have to do to shake that out, we're going to do. One thing that we can do is we can move the 1 plus e to the negative x over to the right-hand side by multiplying. As long as we do it for both the things in the denominator, is 2 times 1 plus e to the negative x. If I'm trying to get e to the negative x on its own, and maybe I'll make a note here. Step 1, isolate this, right? Isolate e to the negative x. If I'm trying to get e to the negative x on its own, then I'm going to divide both sides by 2, right? I'm slowly going to move things over to the left-hand side. So I get 10 divided by 2 is 1 plus e to the negative x. So then I get 5, and then I'm going to subtract 1 from both sides. So I get 5 minus 1 is e to the negative x, which means I have 4 equals e to the negative x. Now, the only way to bring this down, and the easiest way to bring this down, is the natural log. You could use any log, right? But because we've got this e here, it's kind of nice because it dissolves, right? And so we'll take the natural log of both sides. So the natural log of 4 is the natural log of e to the negative x. By the log laws, that negative x gets brought down in front. So I have the natural log of 4 is negative x times the natural log of e. And this is by rule number 3. Now I can solve for x, right? If I bring that natural log of e, which if you use your calculator, right, you should just find that it's 1. The natural log of e is just 1. So just make sure that's what you're getting. But then I have the natural log of 4 divided by 1 is negative x. I have to bring that negative over if I want to be proper. So the negative log of 4 is x. This is the exact answer. So x is approximately, if I take the natural log of 4 and then the negative of that, x is approximately negative 1.3862943661. Were we just too still, or I don't know. Weird. Yeah. That's all right. I don't know. Weird. The light switch is still on. It's obviously not a power outage. I don't know. So weird. We're almost done. I was hoping we'd finish this, but maybe we'll leave some for a review next day. Oh, while I am thinking about it, I didn't make them, Jenna made them this time. I've been making all the notes and then Jenna made them. We're doing like a mashup of chapter 5 and 6 because they're doing the same thing, just 2 different ways. So we're gonna learn them kind of in parallel. Weird. Maybe it was this, learning in parallel. So we're gonna do 5.1 and 6.1 together. 5.2 and 6.2 together, just so you see both the methods side by side. And then we'll do, I think it's 5.3 and 6.4 because they're 2 different concepts, just kind of using them. Yeah.
Is there going to be another kind of practice test?
We're getting together on Thursday to put that together. So you'll have that for the week because your test isn't until the following week, right? So not next week, but the following week. So we'll have that. Yeah. Yeah, and it'll be the same kind of format, all of them, which is a lot, but it kind of makes it doable. Okay. So, of course, this is our approximate answer. Approximate answer. Okay. In the interest of time, I just want to solve one logarithmic equation. So it does go through and it shows you how to solve an exponential equation of quadratic type. You just pretend that the e to the x is just some w squared or a squared or whatever. I feel like that's not really going to come up, so let's just skip ahead to solving logarithmic equations so that at least we've seen all the material, and then we can do a couple of questions for a review next day. But solving logarithmic equations is going to be the same thing, right? Except now you're going to raise the log to whatever base it is to make it go away. So, but the first thing, right, is you're going to isolate the log term, that whatever you want to find with the x in it usually. this is where you might need to expand logs or kind of compress them or combine them. And then you write it in exponential form, right? So you just raise everything to the power of the base, and then you can solve for the variable. And so if we have a look at some of these problems, 49 to 54 is a little bit boring because there's logs of the same base on both sides. So then they essentially just cancel. So I'm going to skip ahead to 55 to 68. But you can go through and try those other ones too. But these are going to be more interesting. So if we try something like number 66, why not? 66, if we've got the natural log of x minus 1 plus the natural log of x plus 2 equals 1, and we want to solve for x, I need to be able to shake out that x outside the log, right? And because it's not in the power, I can't bring it down in front. And so now I need to remember that the natural log is log base e. So if I take e to the power of all these things, then I should be able to shake out that natural log. One thing that just struck me is that because I'm adding logs of the same base, how about I combine those to only have to deal with one log, right? And so first thing I'm going to do is I'm going to rewrite this as the natural log of x minus 1 times x plus 2, right? Multiplying in there because I'm adding on the outside. So this is law number 1. I've got x minus 1 times x plus 2 inside of the natural log. And so natural log is log base e. And so if I take e to the power of both sides, then I'll be able to shake this out. And so here I take e to the natural log of x minus 1 times x plus 2 is e to the power of 1. The reason we do this and use the same base is that this, I think of it as it just kind of drops out. And so it just kind of disappears. Because remember, the rule says that e to the power of the natural log of x is just x. So x just kind of drops down. And so now we have x minus 1 times x plus 2 is e to the power of 1, which I'll just write as e. E is a number, right? But just like pi, it's an irrational number, so it just keeps going and going and going and going. But your calculator's got it, or at least a pretty solid approximation programmed in. So, so now if we have to solve for x, then expand this thing, right? Probably, because it looks like I should be able to get a quadratic equation, so then I can use the quadratic formula. So if I expand this thing, I get x squared plus 2x minus x minus 2 equals e. If I rearrange this, I get x squared plus x minus 2 minus e, right? If I solve this, set it equal to 0. So here I can get x squared plus x, 2x minus x is x, minus, and then 2, oh, no bracket quite yet, minus 2, and then subtract e from both sides to be left with 0 on the right-hand side, right? Because now I can use the quadratic formula. To solve for x. So the -2 minus e I can combine as just one number. And so I get x squared plus x. And then what I'll do is I'll do minus and then 2 plus e equals 0. I'll pull out that common negative out front. And then if I'll just double check to make sure that when I expand it, I still get -2 minus e, which I do. Okay, so now for my quadratic equation, right here, a is 1, b is 1, and c is -2 plus e. I guess I could have had the plus -2 minus e, but it doesn't matter as long as you're keeping track of which is which. So then x is -b plus minus the square root of b squared minus 4ac over 2a. Probably have that memorized by now. We use it so much. Which is -1 plus minus the square root of 1 squared minus 4 times 1 times -2 plus e over 2 times 1, which is -1 plus minus, okay, here we go. Hopefully we get a positive number in that square root. Otherwise, there's no solutions. And so we get 2 plus e. I'll start there. And then negative of that times -4, 1 plus that. I'll just check in here. I get the square root of 19.87312731 divided by 2. I'll just try again. 1 squared minus 4 times -2 plus e. Okay, good. And then if I take the square root of that, I get -1 plus minus 4.45792859 divided by 2. So I get -1 minus that guy divided by 2. Roughly approximations here because I'm already approximating. -2.728964295. And then again, I should have saved it. 1 minus 4 times -2 plus e. Square root of that. -1 plus that divided by 2. I get 1.728964295. I'm way out of time and I'm sorry. We'd want to check to make sure that both of these are in the domain, right? If it's not in the domain, it's not a solution, right? So here's the follow-up. Check that both are in the domain. There. Sorry. Any questions though? So we'll do a couple more of those next day where we're solving exponentials and logs, but that's the general idea. Any questions? No. See you Friday.